Now I wanted to go over another example, just to avoid giving the impression that all critical points either correspond to a local max or local min. We already discussed that, and I'll tell you this was not the case. We have the explicit example of x cubed, where x equals 0 is neither, despite being a critical point, is not a local max nor neither local max nor a local min. But let's see something a little bit more involved. So let's analyze the critical points of the function f of x equals x minus sine x. So as always, let us start by noticing that unlike the previous example, where the function was not differentiable at one point, this is always differentiable. It is infinitely many times differentiable, given that x is infinitely many times differentiable and also sine x, and they're defined everywhere. And what did we say about polynomials and trig functions? They're always differentiable where they are defined in their domain of definition. They're always differentiable. So this is the differentiable everywhere. So the only type of critical points that we can find are points for which the derivative is equal to 0. So if we're looking for critical points, we must solve f prime is equal to 0. But this can only happen if, well, what is the derivative of f? Is 1 minus cosine x. So these are points for which cosine of x is equal to 1. If, in case you don't remember, this is the graph of cosine. So this is 0, pi over 2, pi, 3 pi over 2, 2 pi. And so what happens here is that cosine, and this repeats itself because cosine is periodic, 2 pi periodic. So cosine of x is equal to 0 exactly when x is equal to 2n pi, where n is any integer, where n is any integer. So those are all the critical points of the function x minus sine x. Are they local min or local max? Well, they are not, because remember that cosine of x is never greater than 1. Cosine is between minus 1 and 1. So this implies that 1 minus cosine x is always greater than or equal to 0, right? Okay, so and this is exactly f prime of x. Right? So since the derivative is always non-negative, then the sign of f prime never changes. It never becomes negative. Never changes. Okay, so that means that these critical points are never local min or local max. critical points of f are neither max nor local min. So that's the example where we expect to have multiple critical points, in fact infinitely many of them, but none of them are local max or local min. Okay, so now let's go over some examples where we need to analyze functions using a second derivative. So let's try to go over some examples where we are asked to use the second derivative test, say. Okay, so let's start with the first example. So remember the second derivative test tells us that the concavity of a function depends on the sign of f double prime. Okay, so if you're asked to find the points, say the points of inflection of f of x equals x to the 5 thirds, what do we need to do? Remember, points of inflection are points where the concavity changes from one side to the other. Okay, so what is f prime of x? F prime is equal to 5 thirds x to the 5 thirds minus 1, which is equal to 5 thirds times x to the 2 thirds. What is f double prime then? Is 2 thirds times 5 thirds x to the 2 thirds minus 1, which is equal to 10 over 9 times x to the minus 1 third. Okay, so f double prime is not defined at 0. So f double prime is not defined at x equals 0. So that makes it a candidate for a point of inflection, remember? And that's why I chose this example. Here, f double prime is not equal to 0, the point, but rather is not defined. It's undefined at the point x equals 0. And what we want to check now is whether or not this candidate here for a point of inflection is indeed a point which the concavity changes. Okay, but so let's look at the sign of f double prime of x. Yeah, this f double prime of x is, well, being 10 over 9 times x to the minus 1 third. That has exactly the same sign as x. If you raise 1 to the minus 1 third, it gives you 1, which is positive. Minus 1 to the minus 1 third is negative. So f double prime 0, actually, so it's 0. Oh, sorry. At x, for x less than 0, is negative. So this is negative for x less than 0. And f double prime x is positive for x x greater than 0. So when the second derivative is positive, f is concave up, and when the second derivative is I'm sorry, I got it mixed up. So the when x is less than 0, f double prime is negative, so that means it's concave down. And here, when x is positive, f is concave up. So there's a change in concavity here. So there's a change. There's a change. The change in concavity. Even though f double prime is not defined at the point x equals 0, there's a change in concavity as you move from one side to the other. And so that makes x equals 0 or a point of inflection. Thus, 0 corresponds to a point of inflection. Okay, so now let's go over an example that will ask us to use everything we've learned in these sections. So let's analyze. So let's try to put everything together here. Analyze the critical points of the function f of x. So and the reason I'm choosing this function here is because it's not a polynomial, and it's not one of those wild examples that we just covered. So this is a slightly more complex than the usual polynomial examples, but it's not anything where you will encounter a point for which the derivative or the second derivative are not defined. So this is more, which makes it more likely to be found in one of your exams, either the midterm or the final. So let's look at this function here. And so let's try to analyze the critical points. So the first thing, okay, again, let's notice that this function again is a polynomial times an exponential. They're both differentiable everywhere. So to find critical points again, we simply need to find points for which f prime is equal to 0. And f prime is equal to 0 when, well, the derivative of this expression over here is equal to 0. Alright, so let's compute the derivative. We can use the product rule. So f prime is equal to 2 minus 2x times e to the x plus 2x minus x squared times the derivative of e to the x, which is e to the x itself. And this is equal to, well, we have a common factor of e to the x, 2 minus 2x plus 2x minus x squared. The 2x cancel out, and this gives us e to the x times 2 minus x squared. So this is equal to 0, so then f prime of x is going to be equal to 0 if and only if x squared is equal to 2, or when x is equal to plus or minus the square root of 2. Well, we know that the exponential can never be equal to 0, so we just need, in order for f prime to become 0, then this factor here has to be equal to 0, and that only happens when x is equal to either plus or minus the square root of 2. So those are the only options. So let's try to classify these critical points now using the second derivative test. So we'll classify these critical points. So we'll classify these critical points using the second derivative tests. Points using the second using the second derivative test. Okay, so what's the second derivative of this expression? Well, we take the derivative of the expression again using the product rule. So we have the derivative of e to the x, which is e to the x itself, and then plus e to the x times the derivative of what's inside, which is minus 2x. Again, we have a common factor of e to the x. So we get e to the x times 2 minus x squared minus 2x. Okay? Okay, so then let's try to determine the sign of this expression. So we have we have to evaluate this f double prime, so this expression here, at each one of these critical points. So now we plug in, say, minus square root 2. So we analyze x equals minus square root 2, first, and f double prime of minus square root 2 is equal to e to the minus square root 2, which is positive, so the sign is never going to depend on on e to the x at any point, minus times 2 minus minus the square root of 2 squared, and minus 2 times minus the square root of 2, which is equal to e to the minus square root of 2 times 2. Minus square root of 2 squared is just the square root of 2 squared, which is 2, so you get 2 minus 2 minus 2 square root of 2, so that's going to be 2 times square root of 2, so this is going to be positive. Okay, so the function looks locally like this at minus square root of 2. So this implies that, so this here implies that minus square root 2 is a local min, right? Because the second derivative is positive at that point. Now, if we do the same analysis at square root 2, we get, well, we have to plug in square root 2 on the formula for f double prime. So again, we get this is equal to e to the square root 2 times 2 minus the square root 2 squared, and then minus 2 times the square root 2. Here again, this is going to be equal to 2. So we're going to get 2 minus 2, which is going to be 0. So this is going to be equal to e to the square root 2 times minus 2 square root 2. So this is going to be minus e to the square root 2 times 2 times the square root of 2, which is negative. Okay, if you want, we can write it like this, minus 2 square root 2 e to the square root 2. So this is negative, clearly negative. As I said, e to whatever you plug inside is always positive, but this here is negative, so this becomes negative. So well, if the second derivative at the critical point is negative, that means that the function looks locally like this. So this corresponds to a local max. So square root 2 corresponds to a local max. Okay, so this is this is basically everything regarding the use of this first and second derivative test. And yeah, now we can go over a few final examples, and that will conclude the section 4.3 and 4.4 in terms of material and the problems you may encounter in exams.